Now we will discuss here how a 555 timer is working in Astable multivibrator mode. So it's Astable operation. Astable multivibrator is also called a free running oscillator. As you know that for an oscillator there is no input. So without any input you will get a square wave as output of a 555 timer in Astable mode. Will not have any input. So this is the diagram for 555 timer working as Astable mode. So this is your 555 timer IC. Along with that we have three extra components, two resistors and one capacitor, RA, RB and C. RA is connected between pin number 8 and 7. 8 is VCC, 7 is the discharge. And RB is connected between 7 and 6. 2 and 6 are shorted and we have the capacitor. And pin number 5, normally it is the control voltage. If we are if we are using 555 timer IC in a modulation purpose and all, we will be applying the modulating signal over to the pin number 5. If this pin is not using, we will normally connect this pin to ground through a capacitor of 0.01 microfarad. So normally this is using a 0.01 microfarad capacitor and it will be connected to ground. This is if there is a noise voltage, it will discharge to ground through this capacitor. That is the purpose we are adding this 0.01 microfarad capacitor here. Now for explaining the detailed operation, I'll just go to the with the block diagram or internal block diagram of 555. I will explain it. So this is the internal block diagram. We have the resistive network, two comparators and an SR flip-flop. You'll be taking your Q is the output and actually you are taking your Astable multivibrator output pin number 3 from the complement of Q, that is Q bar, you'll be taking the output. Now this is the NPN transistor we are connecting, that is this pin will be the discharge pin, pin number 7. And this is pin number 8 is VCC, pin number 6 is the threshold, pin number 2 will be the trigger, this is trigger. Will not be using here in Astable multivibrator trigger. Pin number 6 is the threshold and pin number 1 will be ground. Pin number 5 is already I shown here, it is not there in this diagram but it is connected to pin number 5 will be connected to ground through the capacitor C 0.01 microfarad. Now we'll discuss about the Astable operation. So as already I told you about SR flip-flop. For an SR flip-flop, when S equal to 1, R equal to 0, output will set and your Q bar will be equal to 0. If both are 0, Q will be not change. That means here the same thing will continue. And if Q S equal to 0 and R equal to 1, the Q will go to 0, Q bar will go to 1. See here, now initially let it be your output voltage is Q is equal to 0. So I'll just draw the output at the same time waveform, so getting an idea. So this is your output V out. So if Q is 0, V out will be equal to 1. Now see here, when Q equal to 0, this is an NPN transistor. Say I am marking this transistor as T1. So if I want to explain the working, when Q is equal to 0, Q is equal to 0, that indicate that your V out should be equal to 1. So what about transistor T1? Transistor T1 will be off. This transistor is an NPN transistor, 0 comes, it will be off. When it is off, your capacitor C here will charge through the VCC through RA and RB. So your capacitor will charge through RA, RB and C. So I can show that the charging of the capacitor, say I am noting it as TC. Capacitor will charge through RA plus RB into C, and you have a time constant here that I will explain you later, 0.693. Now look at here, as I told you earlier, the voltage coming at this point, that means that will be equal to 2 by 3 VCC, that is a inverting terminal of your comparator. Now here the voltage comes will be equal to 1 by 3 VCC. That will be the reference voltage of your comparator. Now here, when the capacitor voltage is equal to 2 by 3 VCC or just greater than 2 by 3 VCC, it is directly connected to the positive terminal of your comparator. So the inverting terminal voltage is only 2 by 3 VCC. So the capacitor is now charging as it is just exceeds 2 by 3 VCC. Your positive terminal voltage of comparator will increase than 2 by 3 VCC. So suddenly the output of the comparator will switch to 1. When it is switched to 1, S equal to 1. S equal to 1 means your flip-flop will set. So your output now changes from 0 to 1. So when Q will change from 0 to 1, actually your output of triple astable is V out Q bar. So Q bar will go to 0. Q bar will go to 0. Now when Q bar is equal to 0, when Q bar equal to 0, that means Q is equal to 1. So now the condition change. Now when Q is now equal to 1, that means your V out is equal to 0. Your V out is equal to 0. When Q equal to 1, see what about the transistor T1? The transistor T1 will be on. So the transistor T1 goes on. When the transistor is on, it is just like a short circuit here. So your now rather than charging the capacitor will now start discharging. The discharging path will be like this to ground. So the capacitor will discharge through RB through the transistor to ground. It is just like a short circuit now, the transistor, when it is on. So the discharging time of the capacitor is given as TD is equal to 0.693 RB into C. So now this capacitor start discharging from 2 by 3 VCC. So look here, if it is charge going less than 2 by 3 VCC, this is connected to the positive terminal and here is the voltage 2 by 3 VCC. So this voltage becoming less than 2 by 3 VCC, this output again switches back to 0. But even if it is going to 0, this is also 0, this is also 0, that condition your output doesn't have any change. So previously it was in the state 1, it will remain in that state till both S and R are 0, it will continue that state. Now see how much your capacitor will discharge. It will start discharging from 2 by 3 VCC. Now see here, this is again connected to the pin number 2 of the second comparator. That means this trigger pin. So the positive terminal of this comparator is 1 by 3 VCC. Now this capacitor voltage going less than 1 by 3 VCC. This positive terminal voltage will be higher. So then this is now changed to 0 and this is now going to be 1. Reset is going to be 1 means your Q will again set back to 0. Q will again go back to 0. Q is 0 means your V out will switches back to 1 again. So Q Q bar is 1 and this is 0 means again it is going back to 0 here. Transistor will be off, the same will continue. Again it will charge. So ultimately when you are seeing, your capacitor will charge from 1, not completely VCC. It will charge from 1 by 3 because till 1 by 3 VCC only it is discharged. So again it will charge from 1 by 3 VCC till 2 by 3 VCC. So this is 1 by 3 VCC till 2 by 3 VCC. Again it discharges till back to 1 by 3 VCC. Again charges back to 2 by 3 VCC. So this is your capacitor charging and discharging. So this is the basic working of an Astable multivibrator in using 555 timer. Now those who are interested in knowing how we are getting that 0.693, I'll just explain you the derivation. See, time taken for the capacitor to charge from 1 by 3 VCC to 2 by 3 VCC, that is the charging time TC. So at any time I can say that the voltage across the capacitor, so normally I can represent by VC. VC should be equal to VCC into 1 minus e raised to minus t by RC. This is the time maximum capacitor can charge till VCC. But suppose how much is the time taken to charge till 1 by 3 VCC. So we want to find the time taken to get the value to get VC equal to 1 by 3 VCC. Just substitute it and see 1 by 3 VCC is equal to VCC into 1 minus e raised to minus t by RC. VCC cancel. After readjusting I will get it as e raised to minus t by RC should be equal to 2 by 3. Now take natural logarithm on both sides. So we'll be getting us minus t by RC is natural logarithm 2 by 3. So t should be equal to 0.405 RC. So now we will see what is the time taken to charge till 2 by 3 VCC. So our VC should be equal to 2 by 3 VCC now. We'll derive that. So the time taken to reach till 2 by 3 VCC, that is when you are substituting that the same manner when you are doing, you will get t equal to 1.098 RC. Now actually we are interested to get 1 by 3 VCC to 2 by 3 VCC. This is 0 to 1 by 3 VCC, this is 0 to 2 by 3 VCC. So you want to get from 1 by 3 VCC to 2 by 3 VCC means we have to subtract these two. So that is TC is, you will get it as 0.693 RC. And our R is actually composed of RA and RB. So charging time it is RA plus RB. So TC is 0.693 RA plus RB into C. So this is the way we are getting the value 0.693. So similarly for discharging, your capacitor should go below or equal to 1 by 3 VCC from 2 by 3 VCC. So VC should be 1 by 3 VCC and initial charge of the capacitor was 2 by 3 VCC. And the discharging equation is not 1 minus, it is e raised to minus t by RC. So if you are solving that and it is discharging, you will be having only RB and C, not RA. So when we are doing that, we will be getting it as doing the same calculation 0.693 RBC, and that is the discharge time TD. So charging time, as we already got, charging time is 0.693 RA plus RB into C, and discharging time TD is 0.693 RBC. So the total period T will be equal to TC plus TD, that is equal to 0.693 RA plus 2 RB into C when we are adding to this through. F is the 1 by T, and if we are doing that we'll be getting it as 1.44 divided by RA plus 2 RB into C. And the duty cycle is on time or charging time divided by total period into 100. So that is